And so you will see that what are those three different point of views are, and some of them you can do in Fluent. In some cases, you have to write a big UDF to do what you want to do. So it depends on what your objective is. So what I'm going to do is I'm going to show three applications. One is a lubrication. So lubrication is basically laminar flow, very low speed flow, lubrication between bearings, lubrication between clutches and all kind of machinery. And so this will be laminar flow. Then there is a turbo pump where the effect of evaporation condensation will come into play. So that is why I chose that application, because of the temperature effect. So the liquid can evaporate, okay. But in the first one, it is going to be liquid and air, basically water and air. And the third one is going to be a very complex applications, although it will be again the water and air. Is a hydrofoil, just some kind of a small boat kind of a thing going over the surface, and to see what the effect is. So to treat these three different type of problems, you will have to see how you can exploit the ability of the fluent and what you are after actually. Okay. So the cavitation occurs in a fluid, or when it is flowing past. It is a very common occurrence in the pumps and in the turbo machinery, for example. And the reason is that the cavitation occurs, if you have a liquid, and in that liquid, the pressure becomes such, is so low that basically at a certain temperature, let us say even at atmospheric temperature, the pressure becomes so low that to sustain itself, the liquid evaporates into a small bubble. So now what you see here is that this is a very common picture, that in this case of rotating machinery, you see that there are bubble formation. So you have these bubble formation which have two effects. One of them is that it decreases the efficiency of the machine, because the flow is no longer smooth, and these machines are designed for conditions that the flow is going to pass smoothly. And there are other issues as well, because you have, all of them have a casing. They are internal flow, so they have a casing around them. And if you have a bubble formation on their blades, then particularly at blade tips and between the casing, the flow becomes non-smooth, and it affects the vortex formation. All kind of things can happen, complex things can happen that can result into the loss of efficiency. And the second is that eventually these bubbles will burst, and when they burst, they always burst, like if you burst, you know what happens, right? Suppose you burst, which means you are very angry, right? And if you are angry, it is not a good thing. So similarly, if the bubbles burst, I don't mean in particular you, everybody. Don't take it personally, all right? So now if the bubbles burst, then they also can become very forceful impact on this, and that causes corrosion, that can cause erosion, and erosion is a particular thing. And actually, if the pressure differential is such in some flows, then it can actually create a local small shock, which means that the temperature, the variation and the bubble bursting is going to be really not a good thing. So this is what we are trying to address. First thing is, can you calculate cavitation? All right. So that is the goal of this. And this can, as I said, the corrosion, and primarily in this case, the fluid is in most of these applications of centrifugal pump, or you have, turbo machinery, etc. They all have a rotating part. So one of the things that happen is that if you have a rotating machinery, then the chances of the vapor pressure versus the pressure outside becoming so low that you have a chance of bubble formation. This doesn't occur if you don't have a rotating machinery. That's why it doesn't occur that often. And so mostly people associate this problem with the rotating machinery. No, it can do both. You know, the water in general can cause both corrosion and erosion. But in this case, it is the erosion which is going to be the effect of cavitation. So now this is basically explains, what is this process of cavitation is in this chart. So what you see here is that there are three phases that are shown of a particular material. So you have a solid at a certain, this axis is a pressure and this axis is a temperature. And so if you draw a three-phase diagram, it's a qualitative diagram. This is solid and this is a liquid and this is the vapor. And so at a given temperature, let us say this is a close to atmosphere, but it need not be. Then there is a vapor pressure, and if the vapor pressure goes down, then the liquid evaporates into vapor. And so once it evaporates into vapor, it forms a bubble. And so that is the basic mechanism of creating these bubbles. Okay. So now as I showed you, and then of course eventually, when these bubbles enter into the high pressure region, the bubbles occur because of the low pressure, right? And then they can move and enter into the high pressure region on the same blade. Then they will burst. And when they burst, then it can cause, impact. And that impact can result into erosion. And so again, similarly the boiling process, but that is not the subject here. So so what we want to know is that how we can model using fluent, the effect of cavitation. So that is the goal, and you can do it. So now what happens is that how many bubbles do you have? You have thousands and thousands of bubbles. And the second is that not all the bubbles are of the same size. So some have very small diameters, some have big diameters. So we have all these things happening. And the location of these bubbles is all over the place. Some are very close to the boundary, which is the case in general. Some of them move away because of the rotation and move somewhere else. They can move close to the casing. So you have a very complex thing. How do you model this? First of all, that you have to decide how do you model this. So if you say I want to find out the whole mechanism of bubble formation, and then I want to know the detail to the degree that little bubbles, big bubbles, how many bubbles, thousands of bubbles, and I want to know everything about it, then I think in principle, as I showed you yesterday, that if you have a single bubble, you can analyze its behavior, right? But if you have hundreds of thousands of bubbles of all kinds floating around because of this effect of cavitation, then the modeling has to be done differently. Okay. So what is the idea here is that, as I said, that if you have these bubbles, they will impair the efficiency of the machine. So what means that how do they impair the efficiency of the machine? What does the machine contain? Suppose you have a centrifugal pump, a rotating machinery. What does it have? It has a hub and 4 or 8 or 16 blades. So what happens, how does these bubbles impact the efficiency of the machine is that once they have that bubbles, then the flow that is entering, okay, it doesn't look at the blade as a smooth blade, right? Number one. And number two is that the passage between the blade is also changed. So what you are looking at is that what is the effect on the overall efficiency. All right. So that is what you are interested in, which means that you can analyze, what happens to the other parts of the flow that you are interested in. So, what you are interested in is the overall impact of the entire area in some way, that there is air generated, then that is what you are interested in. And then you can say that on the around that air pocket how the flow looks like. So, which means that your modeling capability that you only need is the ability to figure out where the air pockets are. Okay. So, which means that if you take the fluent, all right, and then in the fluent, first of all, under certain flow conditions, it should be able to calculate what? It should be able to calculate where the low pressure is. That is the number one requirement, which it can, because in momentum equation, conservation equation, they can easily calculate where the low pressure is. So, as soon as you calculate low pressure, it identifies that what are the areas where the air is going to be. So, you have to assume that wherever the low pressure occurs, which fluent calculates, all those mesh cells, all the cells in which the air pressure is low, they are going to be source of air or source of cavitation. So, you should be able to do that. You should be able to find that where it is, all right. And then after you do the iteration process, once you have identified that, there is a water moving, and this air in this iterative process, which is a time dependent algorithm, is going to continue to become larger, and also this interface of this air bubble, which you can consider a kind of a all the bubbles together, all right, not individual bubbles, but all the bubbles together. And then how do you basically calculate the interface? The interface between the air and the liquid, how do you calculate that? So, we have a volume of fluid method. So, you can apply the volume of fluid method, the VOF, and then you can say, okay. So, in the iterative process, you start at time t equal to 0, and then once a velocity field is calculated, the pressure field is calculated, then you know in that mesh that you have chosen that where there is going to be lower pressure, and then you know where there is going to be formation of air bubble, which means that this whole area of the grid there is air, and the rest of the grids there is a water. And as you continue with this process, this air water interface will keep on moving, and that means is that somehow you have to account for that effect, and you can use the volume of fluid method. Okay, makes sense? So, that is what actually is required to do that. So, we will basically, and fluent can do it. We do use the same equations that we talked about, and so these are the applications that I am showing you that are the ones that centrifugal pumps, watercraft, propellers, hydraulic turbines, etc. Okay. So, we are going to use a homogeneous model, okay, which is the one that is adequate for this case, and that means that we will basically assume what we have said, that it's a multi-phase in which all the bubbles are going to represent a mass of air in certain part of the flow field, and the rest of it will be liquid. And then the main thing will be that how this interface between the two will look like. So, we will not bother about actually the individual bubbles. I mean, that is what is done actually by the people who are interested in this field, all right. So, but if you are interested in bothered about these bubbles and you want to understand the basic formation of them, and you want to understand whether they are of different size, which they will be, little ones, big ones, then of course there is a way to do it, but then you are doing some, you are killing a fly with almost a cannon, all right, because that's not the goal. So, again in multi-phase flow, I mean, these are the general equations which you have, and which means that this is, you don't have to worry about all these equations, because they are very general, with n number of phases and so on. but we are not really interested in all phases. In our case, we have only two phases, the air and water, and this is a dot, by the way, this is a delta dot, and there is one delta missing here. So there is not very accurate, but there is a delta dot, this is square, and there is a delta here for the diffusion part. So then that delta dot delta becomes delta square, Laplacian. So there is a mistake in this equation. All right. So now, I mean, this slide may be a little bit misplaced, but I just want to tell you that this is a very famous Rayleigh-Placid equation, and the book that Christopher Brennan has, half of the book is devoted to this equation. And the goal here is to study and understand the physics of a single bubble only, all right, and nothing more than that. So how that particular bubble with the pressure difference inside and outside being PV minus P, you can calculate the radius of the bubble, which basically is governed by that, and this is the surface tension. So we will come back to it later, because we are not interested at this point, in this equation, but this is a part of this if you are interested in knowing the bubble itself. And then you have a mass transfer equation, again, like this is a dot here, because this is a scalar quantity and this has to be scalar. So there is a dot here is square. For some reason, this equations, they have. Okay, now there are other details about this, which I will again, I said, I will come back later. Now this is a problem, somebody had asked me, a few days back, what happens if we have evaporation or condensation. So this basically deals with this. So I will come back to it later, but this is, let us just focus on the problem at hand, and that is the flow in a rotating turbine and with certain number of blades with a liquid water entering, and because at a certain places in the flow field the pressure is lower than the liquid pressure, it evaporates into vapor, and that causes the cavitation, and we will assume that all the bubbles coalesce or whatever happens and they form the air pocket. So what you have then is this equation, and this is the governing equation, and so this is the continuity equation, and this is the mixture, and mixture has two parts, that is the gas and the liquid, all right. So standard mixture, this is a conservation of mass, which we have seen before, this is a conservation of momentum, all right. So in this model there is no surface tension at all, so because we are not dealing with individual bubbles. Okay, so there is nothing like surface tension. It's a simple application of the fluent. Also in this case, we are only going to use one equation. So there is not a two fluid model. It is a single fluid, a mixture model. It is called a single fluid mixture model, the simplest one. So what you have is, this is a mixture M, denotes the MEM, and the density. So it is more like the formulation that we had for a nanofluid. Okay. So in case of a nanofluid, the difference was that we had a solid particle of nano particle. In this case, we have the liquid and air. But conceptually, you can say that the way we are calculating density is the gas density times the liquid density. So this is nothing but alpha L, which is replaced by 1 minus alpha G, because the total of alpha L plus alpha G must be equal to 1. This is a momentum equation, which is standard, and here you have again, just like we did for a nanofluid, the viscosity of the mixture, and if there is a turbulent in the flow, which happens actually a lot for a turbine flow, then you have a equivalent of mu mt, which is a turbulent viscosity. And then what you have here is that the turbulent viscosity in the gas and as well as the liquid. Okay, so this becomes, so you have a simple set of two equations. The only difference is that you have these two expressions there. So, if you recall from nanofluid where you had a solid particle and the gas or the liquid, in that case how do you determine that? How do you determine rho L and rho P in that case? How do you determine that? Anybody remember that lecture? These were identical equations that we had for nanofluid, right? Lecture number 4. How did you determine those values? Quick. Huh? No, because you put the nanoparticle and you knew that information. In that case, you said, I have aluminum oxide 2% and 98% is water. So, you knew that because this is the one that you did it. Okay. The only other physical requirement, etc., we are not going to go over that, Brownian motion, etc., we are not going to repeat all that. But there you knew that, and so the answer was straightforward. You had this and this equation because you did yourself. Huh? No heat transfer. Don't worry about that. All the bubbles are together. They create an air pocket. We don't know where the air pocket is. If we knew that, then the problem is identical, and that air pocket is changing. In the calculation process, at time t equal to 0, you calculate the flow field, and that flow field gives you pressure and velocity, and then you know in which mesh cell PV, the pressure is, it has almost reached the vapor pressure, and so air has created. There is air pocket. We don't know. So, what you are doing there is that you are using initially. So, initially tell me what is the value of alpha L and alpha G in this case, initially. Okay. So, initially you are right. So, alpha L in entire grid is going to be 1, and then 0 and 1, 0 and 1, that is the value. But what will happen is in the iterative process is that it will keep on changing, because the air is going to be forming in some places, and so which means that it will no longer be true that alpha L is equal to 1 and alpha G is equal to 0, because there will be places there will be alpha G and next door it will be alpha L. Okay. So, you keep on iterating and you will keep on adding to the air pocket until the whole solution is stabilized. So, it means that it will be a iterative solution of the conservation of mass and conservation of momentum, and now you have to find out this alpha L and alpha G, and alpha L plus alpha G is equal to 1, right. How do you find that out? What is the source? How do you find out the interface, or how do you find out the area where air is there and where water is there? No, that is the reason that you have air, right. I am saying numerically, how do you get this number? If you get this number, you are done. How do you get the number alpha G and alpha L in the calculation process? Anybody? I mean, we are towards the end, I mean, we have done this already, which means that you have to have a method that can deal with the two phases, right. Because now, in the iterative process, you are creating air and you are creating the water, and there is an interface between the two and which is moving or which is changing in the iterative process. Okay. And what is that method? What is the method? Quick. What is the method that deals with the two in a multi-phase fluid? What is the method that deals with the interface? VOF, volume of fluid, or LS, but let us focus on volume of fluid. So, then in order to do that, what you need is one more equation, and this is the equation which is already built into the fluent, and that is the volume of fluid equation. And so you need to solve that. I'm not, you don't have it in your notes, but I'm not going to go over it, but just understand that this is a simpler version of that equation, and this I'm going to treat it when we talk about that question of evaporation and condensation also. So, the volume of fluid method, now you can also take into account by some modeling the effect of condensation as well as evaporation. That is the condensation and evaporation of the air bubbles. Okay. So, this is identically the equation that we dealt with. You remember that? It was d alpha dt plus u dot gradient of alpha. It is the same equation, except it is written differently. Okay. Yeah, I mean the source term is put in because we want to account for some additional effect, and that is that the air bubble can condense or it can evaporate. If you want to model that, then you need the source term. If the air bubble is not going to do anything, is not going to evaporate or condense, then you don't have a source. Yeah. 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 That's correct. Yeah. So the thing is that at t equal to 0, when you start in the iterative process, that is the time you are able to identify by the calculation of the flow field where the air is going to be, in which grid cell the pressure is less than PV. So it is going to be a solution in the iterative process, unlike what we discussed before. Otherwise, because the problem is very different, the only thing same is that it's a continuity equation, momentum equation, and method is the same, that the whole cluster of these bubbles are being treated as one mass of air. Okay, and so you have a certain fraction of air and certain fraction of liquid, but or water, but that is keep on changing in the iterative process. It's not fixed. If you don't do that, you cannot get where the changes are going to take place, right? So that is why, but to find out what is alpha G and alpha L is, you have to solve a VOF equation. So again, what is being done actually in the calculation of cavitation is that you solve the problem just like the nanofluid, but in nanofluid you don't have the interface and you don't have all those problems. It is more complicated. But otherwise, and you just take the solver and say I am going to use the VOF, and you put in the condition that how do you put in a flag that there will be air pocket in this grid when P is less than PV, and then automatically the fluent will change it to air pocket. It has been applied by people, fluent has been used, but I am just giving you the mechanics how do you use fluent. So you have to just say that you have a view. And also I put this thing in because I think you are the one who were asking about evaporation and condensation, and you can account for the effect. Okay, and if there was a turbulent flow, because I think in case of turbo machinery and all that, flow is almost always turbulent, you can calculate the effect of turbulence by using some model. So there is no other purpose of putting this slide except that you have K epsilon model and this model, K omega model and so on. So if you have to account for the effect of turbulence, you should, because what happens is that turbulence does affect the behavior of the air bubbles, and that means that turbulence does affect the region of air versus the region of water. So turbulence plays a very important role, and the flow is always turbulent in case of turbulence. Although even if the Reynolds number is lower, maybe, but it could be, more normally it is couple of thousand or more based on the diameter. Okay, so now I'm going to show you 3 applications that again, as I said, all the applications that I'm showing are from my students. Okay, and so I know that all the steps have been done correctly, which means the modeling, and then the grid independence, and then the validation, and then the calculation. Okay, so I am not going to repeat those steps. Okay, you should have to take for granted, whatever I am going to talking about, that something like this, basically is a transmission of torque. So you have one plate and the other one, and you are transmitting the torque, and in between you have a fluid. And the fluid, so you have suppose a stationary plate and you have a moving plate. All that is simple boundary condition: outflow boundary condition, inflow boundary condition, stationary valve boundary condition. And so this is your model. Almost a homework problem, because it's a very, very simple problem. So what we want to see, and again experiment was done, that you can have various different type of grooves. So you can have a triangular groove, you can have a rectangular groove, and they have a certain, and this was the actual situation in the experiment. So the number of grooves is equal to 20 all around the circumference. Thickness of the film, as I said, is about 0.15 millimeter. The width of the groove is given here, this alpha 1 angle, and then you have the depth of the groove, which is given here, and this is the detail. So this problem becomes complicated in terms of the mesh and nothing more, because you have now these grooves inside, and now then when you generate the mesh, you have to be a little more careful. The boundary conditions are straightforward. The grooves are provided because they help in certain special things that happen, and one of the things that they prevent is the formation of cavitation. Okay, but what we did is that first we had experimental data with grooves and without grooves, so that we could validate it, and then the grooves are provided. So if you go and buy any kind of a HVD device, you will find that they have all some groove or the other, and they have some kind of a circular type of grooves, and people claim that if they have certain kind of groove, then the torque formation, etc., is slightly higher because it prevents the cavitation. So anyway, these are properties of oil and air that we have gone through before, and so we have we wrote a UDF for certain things which were not available in the fluent at the time. And the vapor pressure, that is important to know, a very important quantity, is about 1000 Pascal. Okay, so that the vapor pressure between oil and air, the air vapor pressure at which the cavitation will occur is 1000 Pascal. So that is the value of PV. That is important to know a priori. So what is the atmospheric pressure? Is 100,000 Pascal. And so you can see that how low the pressure has to be for the air, for this air pockets to generate next to the oil. There is no water here, it is oil and air. Okay, and then of course if you account for the effect of the temperature and include the energy quotient, then you can take temperature dependent viscosity by this or some other function. And these are the boundary conditions, as I said. So there is not much to discuss here. So this is the result that occurs after doing what I told you to do. And so what you have is, this is the oil volume fraction at the periodically rotating interface. So this is a volume fraction, and you see it goes from blue to red, and so red area is the oil and the blue area is the air, and this yellow and light blue etc., this is the transition. So, if you do what I told you and you do the calculation using fluent and then you get a periodic solution, then it turns out that at the outer edge of the device there is a cavitation. So, this area you can consider as a cavitation area. This is pure air, this is a kind of mixture of air, and the reason you get this is that the grid that we get, the value of alpha is such that you can consider is this is alpha is pure here. So, this is the air, so alpha is equal to 0, the alpha is equal to 1 here, and in between the alpha has a value of between 0 and 1. Okay. Are you with me what I am trying to do? So, this is the result that you get, and this is the cavitation. The idea is that you want to prevent it. The other thing to see is that how the cavitation changes with the RPM. So, this is at 300 RPM, the upper friction disk has a RPM of 300, and if you go down to 5000 RPM, then you can see that the outer part of the HVD, the amount of cavitation keeps on increasing. All right. And now, if you take that particular plan view, then again get 300. This is a pure air, then this is a mixed part, and this is a pure oil, and this keeps on increasing as you increase the RPM. So, this whole area you can consider as a cavitation, and this is the. So, what is happening is that for the flow conditions and operating conditions that you are interested in, you have developed cavitation for this simple model or simple case, and it is a very good problem. You may think that it looks too simple a problem, but it is a very good problem in terms of the application. So, what it, because it is a part of clutches and it is part of many other machinery. So, what it goes on to show is that the performance of the drive will be deteriorating at higher speeds. So, how do you change that? That is the second question. So, the step number 1 was that not even bother about cavitation, and whatever data you have without cavitation match it. And the second step was then consider the air and oil interface using the VOF, and this is a solution with the VOF, and it is easily doable in Fluent. I am telling you, it is very straightforward, and then you get this particular situation. Now, how do you then rectify this? Suppose you are a designer or you are a person who is working in the industry, then how do you rectify that? No, the temperature, that's a very good answer. Temperature is a part of it, but again there is a bound, So, the main thing is there are certain restrictions there. One is a geometric restriction. You cannot change the geometry. Okay, there is a geometric restriction. It's like, if you have a truck and you say that I want to reduce the drag of the truck, I should make it smooth at the back like a streamlined body. It will work, but then its functionality is gone. What is the function of a truck? To be able to carry your goods, and so that is why it is flat. If you make it smoother, then you cannot carry that many goods. So, the functionality is always a very important consideration. So, in this particular case, you cannot change the size, you cannot change that. You cannot change the operating speed. So, the only thing that you can change, there are certain parameters you can change, is the thickness of the layer. of the oil. You can change that, all right. Or mechanically you can do is that if you change the internal structure by putting these grooves, then it turns out that the mechanism by which all these bubbles are generating, they somehow collapse, and so that's why the grooves were used. So there is a lot more information that is there for grooves. That is for the people who are directly engaged in this work, and who have the data and who have the information. We don't have the data except for the simple triangular grooves. But the people who design these drives, they have a lot of engineers working and trying to do this. Temperature change, yes, there is a temperature variation, and you can account for the effect of temperature. These are done at a room temperature of 300 degree Kelvin. But you can do it, at other temperatures as well, and see what the effect of temperature is. So there are all kind of variations are possible. Okay. So I'm just trying. My main goal is to tell you that by simply using the same kind of model that we use for a nanofluid, you can use that with the addition of the volume of fraction solver. And so it is built in. So this problem is simple enough that if you want to try it, you can do it. And then of course these are the details. I really don't want to go over, because we don't have time. But you can go over, and this is effect of rotational speed on radial velocity, etc. You can have all kind of information that you want, in a non-groove case and case of groove. So now how the effectiveness of grooves is, this clearly shows here. So if you look at 3000 RPM, and that is the one where we have a lot of cavitation, and you see that the radius toward going from the center to the end, you can see how much change is there in the radial velocity. Okay, and that is the cause, that is the main cause that is responsible for cavitation. Now if you put the grooves in radial velocity distribution, the groove region, and then you go back to 3000 RPM here, then what happens? You are here, right? So now you look at this and you look at this. There is a tremendous change in the radial velocity, not little bit. I mean, the range change in the radial velocity is such that it became in the opposite direction because of the presence of the groove. And so that is the reason that you put the grooves in, and that arrests the amount of cavitation. So there are a lot of charts that you will see in your information, that then you can do the detail, why it is happening. So you can see, if you plot the streamlines and so on, they will explain, the reason for the previous chart. So the focus here is just to tell you, how do you do this problem. So I'm not going to go over. This now shows the cavitation region again in the planar area. So if you increase the RPM, then you can see. So and then there are other details to look at. So the whole idea here is to emphasize that you can, and I'm not going to go over all this, as I said, that I just want to, you can read it, in your leisure time if you want, or if you want some papers. So the basic focus here is that it's simple problem where you have a oil film for lubrication, and in this case for transmission of torque. You can generate the cavitation, and the cavitation occurs between the oil, because again the pressure becomes less than the vapor pressure, which is only 1000. And so, and why the pressure changes? Because of the flow. Okay, so you start with t equal to 0, at time t equal to 0, run the calculation, and it will not be periodic in the beginning, and see how the pressure is developing. Then it will keep on pointing out to those cells automatically, and they will become air cells, and eventually the VOF will kick in, and then the VOF will decide how this interface is going to move. But we are not taking into account individual bubbles. These bubbles are all treated as a lump, okay, of air. And that is how people model cavitation today in all industries. All right. If you went with the bubble route, then you will not be able to do this problem, and that's not necessary. So you use, what are you using here is a two fluid model with a VOF. That's all. All right. Anybody has any questions on this? Yeah. Yeah. No. All these bubbles are there. All right. Bubbles are generated because the pressure goes down. Right. Of course, one of the best may be the pressure, not let the pressure ever go down. Okay. But it turns out that in rotating machinery, under operating conditions that you have, because of other benefits, you allow the pressure to go down. Okay. If you don't allow the pressure to go down, like in this case, you can have those conditions that pressure doesn't go down, which means that you can rotate the whole thing at a lower RPM. You can change the other geometric parameters. Okay. And it may not cavitate at all. Okay. Then you are solving an academic problem. You want to solve a problem which is a realistic problem, right? So that means that all the machinery that we use, the bubbles come in. Now we don't know if the bubble is little, bigger, all kind of bubbles may be forming. Okay. We are not interested in all that, because that there will be thousands and thousands and thousands of bubbles. You cannot solve that problem. Your main problem is to know that what area of cavitation is, and from that you can see that is there a way to reduce that cavitation to improve the efficiency. That's all your goal is. Now I don't know what exactly your question was, so does it answer your question or not? I'm not saying that that what happens to these bubbles, how they will coalesce and all that. I'm saying that bubbles are representing the air region, that there is air. That's all. So if you look at in this one, this is a cavitation region. So this is all is oil. This is air. This is a transition. Okay. So you can consider that this part is all bubbles, if you want to consider that. All right. And there's a very simple model, and you can do it. And I think if you work for an industry who is involved in this kind of work, turbo machine and all that, and you can show them that you can do that, I think they will be very happy, because everybody knows that if you went into the study of bubble formation and all that, it's going to be very difficult to do this problem. Okay, so let's try to the other one. Yeah. What is, how it prevents? This one? Yeah. 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 It is related to the pressure. Velocity and pressure are always coupled in any flow. So even in a Bernoulli equation at total constant energy, you know that pressure and velocity is coupled. So if the velocity goes up, what happens to the pressure? Pressure will decrease. So what I am saying is that similarly in this case, if you do the analysis on that basis, okay, you will find that the change in the velocity affects the pressure in that region, not in the same. This Bernoulli equation is not applicable, by the way, and I just, yeah. So then you will find that that has a effect of reducing the cavitation. You can do it. I mean, I am just skipping it. If you want to, take me to Shimla, we can sit down for next 2 weeks and explain to you. All right? Maybe we can ski together or something. Yeah, because that's not important. I am telling you that the thing here is that is not important. Yesterday I showed you a single bubble. The entire phenomena of impact of the bubble hitting each other, etc. Surface tension was the key player. All right. So then there are other problems that we discussed where surface tension is a key player. Here we don't care about surface tension because that's not important. What we are looking for is that the area of cavitation should be avoided where there is an air bubble or the whole air is there. That's we are interested in. We are not interested in individual bubble. If we are interested in individual bubble and their formation, and I said they could be in millions. Yeah, you don't need a surface tension. It takes into, if you want to study each bubble, you can do it, which we did yesterday. Yeah. Yeah. No. No. It is basic. I mean, if you look at those equations, what it is saying is that in the total fluid, let me say it is not even a two fluid model. It is a single fluid model, right? Just like the nanofluid. Nanofluid is a single fluid model. So even though they are solid particles, they are moving as if they are a single fluid. So it is a single fluid model with one continuity equation, one momentum equation. All right. So in this single fluid model, we are saying this much of fluid is oil and this much of fluid is air. All right. But the process of computation of the single fluid model, in which we know how to average with respect to the fraction, we can know how to calculate density, etc. Same as we did for nanofluid. So we are using single fluid model. We are using the single equation, not two set of equations. This is not a two fluid model. But we need to. But we are the iterative process by which we are trying to find how to find the air. You see, when you are starting at 0, time t equal to 0, you have no clue where the air is. Do you know where the air is? So it is unknown. That is why I was telling you that in a nanofluid, you know where the particles are, how much. So when you run the solver, it automatically creates a t equal to 0, some pressure and velocity. Then you use that pressure and velocity at that iteration to say, this is the place we have air. That's it. When you keep on iterating, the amount of air may keep on increasing because now you have a new set of velocity, new set of information. And then when this happens, then you find that as the amount of air keeps on increasing, the interface keeps on changing. Then you kick in the VOF, automatically gets kicked in. That's it. And what VOF, what does it do for you? Nothing more. That it basically tells you this is the alpha and this is the 1 minus alpha. That's all. So it's a single fluid model, and with a alpha to tell you where the air is and where the water is. Is making sense or not? Okay. I mean, maybe it is, this may be a problem, because in a course of 1 week to have so much of material, it is very difficult. And as soon as I give you an application, of course you want to know how that application, the physics of that application, what it is doing, how it is changing the whole thing. I am trying to emphasize here, because of the time constraint, is that what is the numerical model which is able to capture all the physics that you want. Okay. We are not interested in bubble at all. The mechanism of forming the mass of air is bubble, but we are not interested in bubbles at all. Okay. Well, now let me move it. Okay, because I mean, all right. So this is the problem which is a tougher one, the second one. All right. Okay. And the reason I have chosen these problems particularly is so that I can give you as much information as I can, and it is useful. But on the other hand, I mean, there is a lot of variation, that the physics and so on. So this is the problem of the liquid oxygen turbo pump. Okay. So here it is a very different problem. It is a high rotating speed, because just like a turbo pump, as I said, all the turbo machines, etc., and then it has a high inlet and outlet pressure, but it has a very low temperature. This is used in things like a space shuttle, for example, and then it has a compressed structure of inducer and impeller. So now this is the complex structure, this is the grid, and so what you, and this is about 58.8 million nodes. So what you see here is that the structure is such that you have inlet coming to this pump, and thus you have suction chamber which basically draws the fluid, and because of the rotation of the impeller, which is a big blades, and there is the inducer which has a small blades, and then there are of course guide vanes which basically take the flow from the impeller to the inducer, and then it basically goes through the volute, which means to the outlet. And so this is the whole complicated the turbo pump. But the temperatures are very different in this case. The energy equations is extremely important. And so what happens in this case is the effect of evaporation and condensation comes in. So this is the reason that I put that thing in. So the effect of evaporation and condensation comes in. All right. So which means that when you are using VOF, if the evaporation takes place and there is a liquid, then the alpha will change. If condensation takes place, alpha will change. So everything else is same, except because of the effect of evaporation and condensation, because the temperature can make the liquid to evaporate, or otherwise the temperature can take the vapor to condensate. You have to account for that effect when you are calculating the VOF, and that's it. But in this case, again, we are going to assume the rest of this stuff, and that is all those air bubbles, etc. They again create a mass of air. But it's a very, very complicated geometry compared to the previous one, because you have two sets of blades and you have a very complex geometry. Did you get the idea that what is the difference between the previous one and this one? They are acting like a source term, and they have been validated by other people, and they are actually in the book by Brennan also, that for a and they have a fudge factor, that F, if you look at the notes, that F means that depending on the type of liquid and type of the vapor, they need to be fixed empirically. There is no other way to do it. But the equation then has a source term. Other than that, the whole method is the same. Whole method is the same. Okay. So whatever I have said, you can consider that everything is valid. So you treat it as a single fluid, and you have a continuity equation, momentum equation, in which the density is calculated as a fraction of liquid plus fraction of vapor, and then viscosity is calculated as a fraction of vapor plus fraction of liquid, etc. But the volume of fluid equation now has a source term. Now this capability is not influenced at the time we use it. So which means that we have to modify the volume of fluid equation by putting a UDF. But I don't know, the latest version might have this capability. And this is a very important problem, you know, so liquid oxygen turbo pump. And so again, you know, you can see that, you know, same thing, you know, rotor speed and SSTK omega model, and so this is all fluent, as you can see at the bottom, you know. So you know, one of the current theme that you will find in the entire course, except, you know, when we had empirical relation, that I had assumed that everybody here is interested in fluent or focus on fluent. So now, you know, this is, you know, so there is a cavitation number which we didn't define before, which is an important quantity. It is defined always as sigma, and again it is in the book of Brennan, or it is on website, or anything that you look at. It is the inlet pressure to the vapor pressure divided by this normalization constant. So this is the cavitation number. Now the interesting thing is about cavitation number is that when it is 0.20, there is no cavitation, hardly any cavitation. It is just a small change to 0.19. The whole place is full of cavitation. And so this cavitation number is a very important number, you know. Remember when I told you all the numbers, Bond number and Morton number and all that, I did mention to you guys that for some reason, you know, I forgot to add the cavitation number in that slide. This is so sensitive, the way it is defined, because this difference in pressure, a small change in the difference in pressure can make a lot of difference. So this has to be, if it is higher than this, there is no cavitation, and it slightly goes down, it approaches the cavitation pressure, that's it. It can have a massive cavitation. So it's a very instructive slide with sigma equal to 0.20, sigma equal to 0.19, and again it shows more details of it on various parts. This is full of cavitation, and this is impeller, this is inducer, this is suction chamber, and you can do a lot of these plots to show that this is the case. These are the flow on the blades, and you see this whole blades are full of air, and again using the volume of fluid method, nothing more than that. The procedure is identical, that what I showed you. But of course, you have to generate the mesh, then you will have to do the validation, etc. That I have assumed that you are aware of it. I will not show you anything which has not gone through that rigorous test. Okay, it's like, you know, if you want to go to the army, right? What do you need? You will have to start doing exercise, start dieting, or no, I mean start eating the right diet. Okay, you have to be physically fit. All right, but if you want to eat, you know, 100 gulab jamuns every day, you will not be good for army, you know. So similarly here, in order to do this kind of work, you have to be fit, which means that you have to know the whole mechanics, that all those 4 elements that I told you, that geometry, and then grid independence, and then the solution, validation, and then you can see that these results are okay. All right, so all this thing has gone through, and but the main thing is that if you look at the pressure cavitation number, you know, there is this big change. These are all the details, don't matter. Now, how do you characterize this, right? How many of you have heard of Q criterion? So we have one person who has heard of Q criterion. Okay, what is the merit of Q criterion? So if you look at this is full of vortices after vortices, because it's a rotating machinery with the impeller, okay, and then we have a all kind of channel flow. So you have a two set of rotating machine. So it's a very complicated flow, and so it's full of vortices after vortices. So how do you classify those vortices? So people have come up in 2010 what is called a Q criterion, and so this is basically the criterion defines a vortex as a connected fluid region with a positive second invariant of delta U, a gradient of U. So this is defined in terms of the velocity gradient, and this helps in basically identify. So if you have a bunch of vortices and if you have a velocity field calculated from fluent and the pressure field, you take its gradient, and that will give you some idea that where the vorticity is. All right. Okay. So now can you tell me why the gradient of U gives you the vorticity? It's a basic fluid mechanics. So if you have, let us say you have a plane, and the plane, the fluid is rotating about a z axis, and you have flow in the U and V, right? There are two components of velocity in the plane, U and V, and the third component 0 is a planar flow, and it's rotating about the third component, that is in the z direction. What is the equation vorticity? Anybody remembers what is the equation of vorticity? Curve velocity, that is correct, del cross U is equal to 0. So if you simplify that, it turns out that it is dv dx minus du dy in the for the z component or z component. So it turns out that if you take the gradient of velocity as a simple measure, it is somehow captures where these gradients are largest, and they are largest where that is where the vortex is. Now in case of, suppose you have a flat plate, right, and the flow is coming in, the velocity here is 0, right? Where is the maximum gradient of velocity on this plate? Very close to the, so where is the maximum vorticity in this flow field? Right on the wall. So the gradient is a measure where the vorticity is going to be sitting in. It's a very good qualitative measure. So if you have calculated the flow by using fluent or any other means, you can just take the gradient, and then that is a measure, and people have done that, and that is what is called the Q criterion. And so you can see that the vorticity is areas where the vorticity magnitude is greater than or magnitude than the strain. So strain is the same thing as vorticity, right? Similar to that. So that is a Q criterion, and it is very heavily used nowadays in characterizing the region of vorticity in three-dimensional flow. For a long time, although vorticity has existed from the beginning of fluid mechanics, tornadoes and you say name it, everything has a vorticity, even a plate has a vorticity. People did not know how to do it well. So when this visualization came in, and the visualization software came in, and a lot of these people who work with this kind of a thing, how to characterize the flow field, and I don't know whether ParaView people are also in that category. Then they figure out that if you have delta U, you can do this, and somebody called it a Q criterion. There is a delta criterion, there is other criterion, but this is just a name. So now you see here, the Q criterion, and I don't know whether, so you see here, if the Q criterion, which is based on this, so this is sigma is equal to 0.20, and this sigma is equal to 0.19, and of course you can see that in this case where the cavitation is hardly there, you can see that the vortex flow of course is going to be there, because the flow is entering the and this is full of vorticity. See that how much vorticity is here, because there is a cavitation. And so Q criterion here 0.003 is 0.01, is 0.02. So what it means is that if the value of Q is small, the vorticity is less. If value of Q is large, the vorticity is large, and that is because of the gradient. So this is very widely used actually. So in this particular calculation that was done, this is all kind of Q criterion level and all kind of cases that were run. Again, I am not going to go into this, and then you can see this is a final chart, that is the vorticity is generated, and there is a blue line and the yellow line, and if is a sigma is 0.19, which is the cavitation, you see this, and if it is 0.2 is this one. So what you find is that the vortex region, which is full of cavitation, is about 43% when of the whole region if the cavitation is full, is 0.19 number, and if it is 0.20, it is only about 20% or 18%. So this is a good way to see how the cavitation is working and how do you characterize it with the Q criterion. So basically this is other case. So what is the difference in this case with the first case? The only difference in using the fluent, and this is done with fluent, is of course the temperature is a very important part of it. It is grid wise is absolutely nightmare compared to the first one. First one very simple, 2 disks. It was a simple example. Here in terms of the grid was difficult, but let us forget about it. Same fluid model, single fluid model, continuity equation, other stuff, momentum equation, all right. Same approach in defining the region of air versus liquid. What is the difference is now evaporation and condensation is taken into account. So the VOF, you have to put little more work to be able to allow for the condensation and the evaporation, but nothing more than that. The entire bunch of bubbles is considered as one single lump of fluid. What? No. Those things, now you are going at a different level. Now, no. If you have a rotating machinery like helicopter or you have a propeller, then what you are talking about is basically the grid and how do you impose the boundary condition, whether you use the rotating coordinate system, etc. We are not going there. That is totally different aspect of it. All right. We are just focusing on two-phase flow. We are not focusing the entire, Ramayana here. We are just doing some small part of it. Okay. Anything else? You got the message here. So we are not considering individual bubble. But the other thing very important, I think you should get out of it is that how do you characterize the vorticity? All right. So if you want to use this, just take the boundary layer on a flat plate, and it is full of profiles as you move, change in profile, because there is a boundary layer thickness, and therefore the gradient changes, and use that gradient delta U in 2 dimensions to see how Q changes from here to here. So suppose the flow is coming from that side, boundary layer thickness there is how much? How much is the boundary layer thickness there? 0. And here it will be delta, some function of Re. So if you calculate this vorticity, which means profile will keep on changing because there is a delta here, Q will keep on changing, and then you plot Q along the surface. It will be very instructive, very useful. So I think that some of these ideas which I am talking about in a very larger context of multi-phase flow, you should try it and for simple problem and see what happens. I think always try a simple problem and see what happens. So I think that I just want to do the third one, and this is the one where it is going to be very complicated, but it has a lot of information that you cannot do by fluent. But here you can do what you might be thinking, if you want to go into details. So now suppose you have a flow, all right, and in this case we are considering the flow over a hydrofoil. The goal here is that again there is a cavitation. There is a liquid and air. So hydrofoil, other medium is air, and you generate bubbles because of cavitation. Now our goal is the detailed information. This is a completely academic problem. Our goal is not any design or any industrial application. So now we want to say the bubbles are little bubbles, big bubbles, bigger bubbles, all kind of bubbles are there. And we say there are 200 bubbles. And how these bubbles are distributed from little diameter to big diameter. And mostly it is Gaussian most of the time. You want to take into account everything. Okay. So in order to do that, you have to use a statistical model. Okay. And that is called the population balance model. And for that you will have to write another code. Okay. And even if you are very smart, it will take you 2 years, because it is based on very, very complicated set of equations. But I wanted to give you this example, not to impress you, but to tell you that if you want to go into that much of depth, that you want to consider the cavitation for a small bubble, big bubble, etc., then you can do that if that is your goal. And then also there is experiment, also you can do if you have all the equipment to do that. Okay. So this is that example here, and what you find is a hydrofoil, and again you start with this main code is fluent. So you have this Clark Y hydrofoil, and this is a thick aerofoil. So in contrast to the wing that you have in air, they are very thin, and if you are fighter aircraft, they are even thinner, and if you go into the water, they are thick. So there is a thick aerofoil, and this is a very famous aerofoil, Clark Y, and this is a cavitation number, and so you can mesh it, and then these are the data on this aerofoil, and this is a computational domain and boundary conditions, and this is cavitation number, and again this is a fluent. So you can see that all these turbulent flow, turbulent model and all that. Okay. And this is again, now here we are going to use a two fluid model. Okay. We are going to use two fluid model. Previously both the examples had a single fluid model. Which one? Yeah, I mean, yeah, we are using, but you can, in this particular case, because the Reynolds number and Mach number that we are simulating is a little higher, it's better to use compressible. But you can, but if the Mach number is lower, then you can use incompressible. That doesn't really matter. Again, pressure velocity coupling doesn't matter. In general, the thing is that even if you have a compressible flow and you use a pressure based solver, you will get an answer, a reasonably good answer. But if you want to get a better answer, you use a density based solver. Okay. So originally, if you go back 5, 6, 7, 8 years, Fluent itself, for 20 years had a pressure based solver. So suddenly, they thought they want to improve, so they put a density based solver. So it is always a evolutionary thing, it is not cast in stone and cast in time. So tomorrow, something else may happen. So all these turbulence models are there. Do you know that until 1984-85, only models that were used were K epsilon, right? And before 1970, all the models that were used were zero equation models, like CBC, Smith, and Baldwin Lomax. Because even if you have this model, what do you do? And until 1940s, not 40s, the 1980, nobody could even touch to solve the Navier-Stokes equations. Okay, the computers were not there. And if that would have been the case, that computers were not there, we won't be here, right? This course will not be offered, and we will not be here, and we won't meet each other. right? Maybe you may say that would have been a good thing, right? The point I am saying is that everything is evolving. If you go back to the Wright brothers plane, I won't be here either, or I won't have ever gone to America actually. The point of this is that even the technology at all level, algorithm level, turbulence model level, everywhere it is evolving. Okay, but the point here only is that we have this particular solver, and here we are using Euler case. So Euler means there is a two fluid model, and we are treating the equation for the air and water separately. Okay, previous cases we did not have that. All right, and of course y plus etc. So now this is the thing. So what we have, this is the actual situation that will occurring. We have a little sphere, a little bubble, bigger bubble, and all that. But every time, previous two cases, and some cases in general, even if you want to account for bubble, they treat them all spherical bubble of the same size. That is, they are monodisperse. Very rarely that you can deal with this. And the previous cases that I showed you, both the cases, we took all of them together and considered as a big mass of air. All right, and that was good enough. So now if you take these bubble of this type, they can break up and they can coalesce. So you can even account for that. This you cannot account unless until you take into account the effect of surface tension. And then if you take a general distribution, they all look like this, and then this is normally a Gaussian distribution. So now in this case we are taking into account everything. The bubbles are little ones and bigger ones and all that, and they form some kind of Gaussian distribution. So this is an academic problem in the sense that we are going to only deal with 10 bubbles. We cannot deal with 1 million bubbles, because of the scope of the problem. So idea here is to see that if the bubbles are of different size and they follow a Gaussian distribution, then how you can solve this problem in terms of getting some more information of flow over a hydrofoil, which is our geometry, and the flow of the mean flow of the hydrofoil is calculated by ANSYS. So now what we do is that we use the population balance method, which basically defines all this. Okay, and that is based on the statistical theory. We will not go there, and in this case what we are going to do is that we will divide all the bubbles into 10 groups. So as I said, that group number 1, group number 2, and group number 1 will have so much of diameter, which is very big, and then we will, which means 6.4 times 10 to the power minus 5, and it will keep on going 10. So otherwise the problem is not manageable. If you have 1 million bubble of all different size, you cannot do that. But here this is good enough, and this is the equation that you need to solve. So now birth rate due to coalescence, the death rate due to coalescence with other bubbles, the birth rate due to breakage of bubbles, etc. So it is actually based on what is analogous to the Boltzmann equation. It's extremely complicated. Okay, so as I said, if you do it yourself, it will take a long time to solve this problem with this sample of bubbles that I showed you, and they follow the Gaussian distribution. Huh? What is that? Which term? This one? Yeah, so has anybody ever seen the Boltzmann equation? Okay. If you have not seen, go and see it, which means everything is available. This problem is solved in two spaces. One is called the physical space, and another called is the velocity space. So to analyze the movement of these bubbles, it requires, just like the movement of molecules in the air, which is modeled by the Boltzmann equation, it has the velocity, the Cartesian space or the physical space, and then the velocity space. In the velocity space, it defines the movement of these. So the velocity space has also three components. So this guy here, which is has a this little v there, sub v, which is indicative that these gradients are not taken as ddx and ddy and ddz. They are taken as ddu, ddv, ddw. So this becomes a velocity space problem. So that is why I was saying that the solution of this equation by Boltzmann equation is extremely complicated. So that is, but this is a good question actually, because you looked at the notation and you were wondering what does it mean. So this means that this gradient is done and solution will be done in the velocity space. Okay. Now all this is done on a Cartesian grid, by the way. So there is no grid generation here. So now again the validation, if you look at it, and there is a validation available, and this is basically ANSYS solution. And so what you see is a blue one. So blue one is, the cavitation is 2.4, which means that there is no cavitation. Okay. But then if you have a lower value of sigma, then there is a cavitation on this hydrofoil. Okay. So for this particular case, the cavitation number is very different than what we had for the case of pump, previous one, where we had 0.19 and 0.20. And then you see that this is no cavitation and this is a cavitation, and this is the cavitation has started. So these are basically lump of bubbles which is showing the cavitation. And then it turns out that that there is a periodicity in that solution, and in case of cavitation, and so the lift and drag over the aerofoil is changing in this fashion. So you can get all this information, and this then goes on some more detail that how this cavitation is changing as you go from T0 to 1.0. Okay, and these are details of vorticity, and again you can create a Q criterion, and then you can see that bubble fraction in the flow field is changing. And now you can see, this is an interesting slide, that how the diameter of the bubbles is affecting the bubble fraction. So now the bubbles are not of the same diameter, they are changing, and we had 10 samples of that. Okay. And these are some more stuff. So that if you can take these bubbles and define the volume fraction together, then you have this alpha v, and so you have different type of volume fraction, because some of them may turn into vapor. So you can have all those details if you are interested in. And this basically shows that how the coalesced part of these cavitating hydrofoil, they look. So this is again the all of this is the periodic solution of the cavitation. Okay. So the last case actually goes on to show that it's possible to do the problem in the entirety if you couple the ANSYS solution with the Boltzmann equation. And that means that you can take the sample of bubbles from very little to very big one, and then you will have to see how they move, and their movement in the physical and velocity space is defined by the movement in the Boltzmann equation. And the mean flow is still calculated with a turbulence model by using the ANSYS. And that coupling is not that straightforward. Coupling is quite complex, because the way the Boltzmann equation in the velocity space calculates the movement of those bubbles is quite complex. But I just wanted to show you 3 steps. The first one, which is the most common engineering problem. The second one is also a common engineering problem with evaporation and condensation. And the third one is a problem which is that if you want to capture everything, that is the nature of the bubbles, the type of bubbles, and how they affect the cavitation, then it becomes a very complicated problem. So actually anything you want to know about cavitation in totality, if you go over this, even on a peripheral basis, I think you will know a lot that what is involved in the cavitation and how you model it. Okay. So let's close it here, and we have a couple of more presentation, but I think I will cover maybe one more. Okay. Any question? Okay. So I think that we can have a break and then come back.